Welcome everyone to today's webinar. So today we have two speakers, and the first one is Halil Ibrahim Bayrak. So Halil is a postdoc researcher in the chair of decision science and systems at the Technical University of Munich. His research is in the intersection of robust optimization and mechanism design, with a focus on the decision making under uncertainty for allocation, inspection, and pricing. He did his PhD at Bilken University in 2022 and was a visiting researcher at the University of Pennsylvania. So Halil, it's a pleasure to have you here, and without further ado, I want to give the control to you.
Thank you very much for the kind introduction, and thank you for the invitation. So I'm happy to present our work here, and I'm looking forward to your comments. And this is a work I did here in my postdoc with Professor Martin Bichler. And let me just start with our motivation. So there has been a news story. This is dated 2022, and it is about this Amazon, the big company. And Amazon has this fulfillment by Amazon services for its services in its online platform. What it does is sellers, if enrolled in the services, use the capacity store of Amazon for their inventory, and then when an order is received, Amazon also handles the transportation. And also, if there's a complaint, Amazon also does the returns, customer services, and so on. And in this story, it says this capacity is, of course, limited. And in 2022, many sellers in this platform complained they couldn't get the capacity they would actually like. And then there was a follow-up story a year later. So apparently Amazon turned this allocation problem into an auction. So they collect bids from the sellers in this platform and then starts allocating these capacities one by one to the highest bidder until all the capacities used. And then there is one unique twist here. What happens is they look at the performance of the sellers who were allocated a capacity, and if they made good use of this capacity, if their performance were good, then they gave back some of the money, or even it was possible for recouping all of the fees they paid for the sellers. So let me give you as a timeline what happens. So there's Amazon with this FBA services, and let's consider only a single seller. This seller privately knows this $T value, which you can think about this future sales. They think they would make. This can be a forecast, and then they bid some value. This can be different T prime dollars, let's say, and then allocation makes Amazon makes an allocation decision, and then this FBA services are used. And thanks to its online platform, Amazon, and also the seller can see the performance while they use the services. And this can be of another value, T double prime, let's say. And according to this observed information by Amazon, note that Amazon only observes the bid, T prime, and the performance, T double prime. According to these values, Amazon gives some reward back to the seller. And here the first part is just a classical auction, bidding and allocation decision. And then modern tools today give us more possibilities. like online platforms or point of sale systems. We can also use this, what I will call as formally like costless deferred verification. We can verify the actual sale, and we can also give back some rewards. And including these two tools, the question is, can we improve the expected revenue from an auction? The optimal auction literature was well researched, but these two tools brings a new setting that requires some research, and there has been a paper who actually addressed this problem and answers this question affirmatively. So yes, we can increase the expected payoff very much, and you are seeing here on the left side the allocation rules, and on the right side the payment rules of two mechanisms. The mechanism in red is the classical optimal mechanism, which is called posted price mechanism. And the blue one is the mechanism with inspection and rewards. And here, as you can see, the allocation also changes a lot, like the low types also get here partial allocation. The partial allocation can also be taught as probabilistic allocation. And the right-hand side, you are seeing the payment. Every type just gives a deposit equal to its own value. This dashed line is the deposit, and then this green shaded area is the rewards returned back. And what is left to the platform is this blue line, the payment of the auction. And when we look at the expected values of these two optimal mechanisms, posted price yields 0.25, and this is when the type of the agents are between 0 and 1 and uniformly distributed. While if we use also inspection and reward rules, we get 0.38. Like this is about 50% more expected payoff we can get using these two tools. But the important thing here is that we have to know this distribution of types for the agents, and this mechanisms allocation rule and payment rule is tailored specifically to this distribution knowledge. And most of the mechanism design literature, it is standard approach to assume a type distribution, but this is also criticized because like in real application, this is very hard to know the exact distribution, and an ambiguity in that side would lead to suboptimality if we use such an optimal solution. And that is why here in our paper, we consider the distribution a robust setting. So we assume the seller only knows the first n moments. And like here, you are just seeing the mathematical notation. This calligraphic P, K is the ambiguity set. All distributions for the type set, support sets 0 and 1, satisfying the moments are admissible. Here the moments are given by ki values, and this both k is the vector of k values. And we assume the seller wants to maximize her worst case payoff. And we extend this problem in the hopes that we find a more applicable mechanism under this assumption also. And before showing you my model, let's recall what I will introduce with this slide, the mathematical notation. The mechanism design problems are in general very hard to solve. Like we need to come up with this allocation rule X and reward rule R, and on the other side, while we are solving a maximization problem with respect to finding a mechanism, the single agent can also has its own maximization problem, maximizing her utility using a best response function, which depends on her own type, knowledge T, and the allocation we choose. So solving this problem is very complicated, but thankfully there is this revelation principle result from the mechanism design literature. Simply it says we do not need to consider complex mechanisms. It is without of loss if we just consider truthful direct mechanisms where the agents do not strategize, they just report us their true type T. So there is a simplification here which makes our life easier. We just optimize over the mechanism, choosing the allocation rule X and reward rule R. Here what happens is true type revelation, and we decide on an allocation, and the inspection just reveals the true type. So we give back the reward according to this type T. And it is also instructive to consider what happens when the agent reports something else that is not equal to their true type. And in this case, we again allocate, but with respect to the false type T prime. Then the inspection will reveal us that this report was false. So in this case, we return no rewards because we are only interested in the truthful revelation. Then I am ready to present our model. So here first, I will present the one with the knowledge of type distribution. So we are maximizing the expected payment, and payment here is the deposit minus reward, what is left to us. And we can change the reward rule and instead just solve for the payment rule, which are like we can recover rewards at the end. The first constraint is just allocation should be feasible, a probability between 0 and 1. And we have here this individual rationality, IR constraints. It means every type, the utility from allocation minus the payment should be non-negative. And in the incentive compatibility, this IC constraints, this means our mechanism should be direct. So the left-hand side, the truthful revelation utility should be bigger than or equal to any utility the agent would receive from falsely reporting their type as T, some other type, any type T prime. And here they get the allocation according to T prime, pays the deposit T prime, but do not receive a reward. And yeah, this is the distribution robust model. We just changed the objective. Now there is an adversary trying to minimize the expected payoff we get by choosing a worst case distribution in the ambiguity set. And I will refer to this problem as DRM. And yeah, here you are seeing after some simplifications which were already appeared in the Halil paper. It turns out the IR constraints were redundant. They were already implied by the IC constraints. And the remaining IC constraints, they just turn out to be upper bounds on the payment rules. These are some easy steps. I omitted I have the reserve slides if you are interested. And there is also another result from another robust mechanism design paper, Carrasco et al. From 2018. They solved the classical single agent case without the inspection and rewards, and they consider the same ambiguity set with they know the moments, first n moments, and here it seems complicated, but I will guide you to read this result. It says, let's consider a payment, which is nice. I mean, it is bounded and it gives a non-negative worst case payoff under our ambiguity set. And also assume that there is some worst case distribution, P star, which actually attains this worst case expected payoff. And then they show that there exists this lambda coefficients from 0 to n, the vector of lambda values, which are actually a polynomial coefficients. Here you are seeing the polynomial of t, and this polynomial with lambda coefficients are actually they lower bound our payment rule for all t, and this happens almost surely with equality under the worst case distribution P star. So yeah, we also have this seller's revenue equivalence. So under the worst case expected payoff from the payment rule is just the weighted sum of the moment informations. How this is useful is like since in our model the payment rules only have an upper bound, it has no lower bound. So instead we can just use this polynomial payment rules, a simplification of the model, and then this would still be robustly optimal. And here this first result in our paper, and this is for the case single agent and first moment, and we denote the first moment by mu. What this result means, like there is a worst case candidate worst case distribution consisting of two points. Like it puts probability mass into 2 points, the highest type 1 and a type slightly less than the mean value. This is mu over 2 minus mu. And this low type also upper bounds the expected highest payment we can get. So under this distribution, this is an upper bound for our robust optimal mechanism, feasible mechanisms. And our first result, so this also looks complicated, but the first part, you don't need to pay attention to this first complicated nonlinear optimization model. This cannot be solved in closed form because you have to solve a 8-degree polynomial. But this is necessary, and we solve this numerically to get a boundary, this P prime, which bounds which gives us this bound. Like our proposed robust optimal mechanism is only feasible beginning from this P prime value until 1. And this robust optimal mechanism, this is the important part, consists of a weakly increasing allocation function and a payment rule which is just linear. Since we only know the mean value, this is polynomial of degree 1, which we already covered. It is enough for robust optimality. And also this our mechanism gets the upper bound we already seen in the previous slide, which was the mu over 2 minus mu value. And this is the figure, like the mechanism drawn for 4 different mu values. This dashed lines are the payment rules, and the straight line, the concave above lines are the allocation values. And here, as you can notice, some low types make negative payments, which means actually principal subsidizing them. And this is actually not necessary because like the constraint, the upper bound we have is actually always non-negative because this X allocation value we propose is weakly increasing. You can check this out. So what we can do is we can just get rid of this negative parts, set these parts equal to 0, and still get feasibility, and we just increase the payoff under non-worst case distributions. So it is still robust to optimal, but has better performance under other distributions. And this also means that I can take convex combinations of these two different mechanisms and end up with infinitely many robust optimal mechanisms. So robust optimality is not enough to get a good solution. What we do is we also borrow this Pareto robust optimality definition, and for our problem, we also propose a robust Pareto robust optimal solution. Here, just I want to quickly go over its definition. So we first define weakly Pareto robust domination. So a solution weakly Pareto robust dominates another one if its objective is always better than another one for all admissible distributions, and it Pareto robust dominates this solution with prime if it weakly Pareto robust dominates it, and also there exists a distribution so that its objective is strictly higher than the latter mechanism. And lastly, we can define this mechanism is Pareto robustly optimal if it is robustly optimal to begin with, and there shouldn't exist any other feasible mechanism that is Pareto robust dominating it. And now the Pareto robust optimal mechanism in our case is that it has the same allocation rule, but the payment that extracts the maximum feasible payment, this would give us Pareto robust optimality. What do I mean by maximally extracting the maximum? You are just doing this. The payment should be equal to this tight upper bound in the constraint. That the proof is not trivial, but still what we get is a complex payment rule, as we can see here for the previously presented 4 cases. It is always better than the linear. It is always non-negative, but it might be complex to implement this also. And this is a summary of our proposed mechanisms with the standard mechanism with the distribution knowledge. What we propose is like one of the mechanisms is simple, robustly optimal. The other one is also has complex payment rule, but it is guaranteed to be Pareto robust optimal. And here you are seeing the numerical experiment we have done compared to the what we do is we take convex combinations of the uniform distribution and the worst case distribution and the contamination level. When it is maximum, we are at the worst case distribution, and our proposed mechanisms are actually optimal. On the other extreme side, we are not optimal, but we are still very close to the optimality. Even the linear simple mechanism with linear payment case, this is also not very far away from the optimality. And when the contamination levels increase, we outperform the standard mechanism. Yeah, and main contributions, there was also the multi-agent case that I didn't have time to present, but what we do is we extend the polynomial payment result to multi-agent case. The difference is the payment is now, the aggregate payment from multiple agents should be a degree n polynomial. And we look at the first moment case, this aggregate payment being degree 1 multi-dimensional polynomial. This doesn't simplify the problem much, and we only give some numerical experiments illustrating the optimal mechanism and discuss its complexity. And I have already covered the single agent first moment case that we give robust optimality Python, robust optimality and numerical results. I think I don't wanna go over so long. So that was all from my side. Thank you for your attention.